In this video, we're going to return to calculating competitive balance measures to back out what the implied odds of becoming a champion for the season is for each team, and use that to construct the competitive balance measure that was discussed in McEwen and Metz. So first off, we want to open up the data, and let's just take a look at it. So as you can see here, we have payoff data, which is basically read as saying how much money you would win for placing a $100 bet on this team to win the championship in that year. So for example, here we're looking at the Denver Broncos, and the payoff is $600. What that means is if you bet $100 at the beginning of the season that the Denver Broncos would become champion or win the Super Bowl in 2013, you would win $600, which includes the 100 you bid. So you get your 100 back plus $500 profit. That's the way we read it. So in 2013, it looks like the Denver Broncos must have been the favorites to win because you would have received the lowest payoff for them. As we go down this list, the payoff gets larger, meaning the likelihood of this team winning the Super Bowl is decreasing. Let's see what the worst case scenario is here. So it looks like almost nobody expected the Jacksonville Jaguars to win the Super Bowl, and of course they didn't. But had they won the Super Bowl and you placed a $100 bet on them in 2013, you would have won $20,000. That's how unlikely it was. Or at least according to Vegas and everybody betting on the Super Bowl champion at this time. Now we're going to focus on the 2013 NFL season first, but just to show you, we do have more data than this. If we look at our variables, you'll notice that we have a league variable, a year variable, payoff, and team. If I tabulate league, you see that we actually have the 4 leagues discussed in the paper. We have Major League Baseball, NBA, NFL, and NHL. If you look at the years, I have downloaded the payoffs for 2013, which is in the paper, and then the next 5 years. So what we're going to do here is try to recreate part of the analysis that was done in the paper with more recent data. This is a good example of what you could do for your project. You could find a paper that you like, take one piece of it, one small little piece, you don't have to do the whole thing, and see if the results still hold with more recent data. This is actually a useful exercise to do, not just for you to learn, but also for the science in general. There's not a lot of journals that will publish what's called replication studies. So what we're doing here is replicating the results of the paper to make sure that they still hold if I use a different data set. We're checking to see that it wasn't just the case that that particular data they used gave them the results they got. More of this is needed in science, especially in economics. Because if we don't do this, we might only publish papers that have really strong results or really unexpected results, and those might not be robust. That is, it might just be by chance that you stumbled upon a data set that gave you a certain result. It's good to check the logic and the theory or the process on many data sets to make sure it's consistent. So before we get started, I want to say that if you want to challenge yourself, I highly suggest you reading the PDF and attempting to do this on your own. By this point, you already have most of the tools you need to complete this. And so if you read the PDF, you'll see I don't tell you how to do any of these things. I just tell you what to do. I give you a path you could take to complete this. It's not the only one. It's just the way I do things. But I don't tell you how to do it. So I would strongly suggest at this point that everybody try to do this on their own before watching this video. But if you get stuck, feel free to come back and I'll tell you how to do it. Okay, so the mission here is to recreate figure 1 from the paper with this new data set. And here's the figure again that we're trying to replicate. As you can see, the last year in this figure is 2013, and we do have that data, but we're going to continue this graph into the next 5 years. The reason I kept 2013 in here is so that we can check to make sure that the calculations we make are the same as in the paper. That way we know we're doing it correctly. And we'll use this table 1 here to make sure that our numbers align with the paper. This is what we should get for the NFL in 2013 for the probability that any team would win the Super Bowl with the juice removed. And remember that juice is the percentage or the fee that the casino takes. They're not going to offer you a fair bet because they wouldn't make money if they did that. Imagine if I offered you a gamble of flipping a coin. If you guessed heads or tails, you win. If you bet $100 on a coin toss, and I say I'll pay you 2 to 1 because the odds of you getting it right are 50%. That is, you'll get $200 if you guess right, and you guess heads, and then I go out and find somebody else to guess tails. You both give me $100. Well, those are fair odds for both of you. Those are fair payoffs, and whoever wins gets the $200. But meanwhile, I, as the casino, receive nothing. So what I would do in this case, if I were a casino offering odds on flipping a coin, is I would offer to pay you perhaps $190 if you guessed right. In that case, both of you give me $100. Whoever wins gets $190, and I pocket $10. But if I backed out what the odds are of winning a coin toss from the payoff of $190 versus the $100 bet, I wouldn't get 50%. And so that's the logic behind why we have to remove this fee, or what's called sometimes the juice, that the casino squeezes out of the gamblers. And when we do so correctly, we should get these numbers here as they did in the paper. So let's get started. As you can imagine now, my suggestion is going to be to start writing this logic in a do file. And I'm going to do so here for just the year 2013 and only for the NFL. So in this way, I'm only focusing on writing the logic for pulling out or extracting the implied odds of victory from the payoffs. I don't want to have to worry about doing everything by team, by year. I just want to focus on that one piece of logic. So what I'm going to do is say keep if league is NFL. That's the only one we want to keep. And year equals 2013. Now I could have said drop if league is not NFL and year is not 2013. There's many ways to do this. Here I'm just saying keep what we want. And if I tabulate league and year at the same time, I can do that. We see that there are 32 observations, which is correct. There's only 32 NFL teams, and the only year is 2013. So we're good. Now, following what the paper said, we first want to get the odds from the payoffs. So again, if I look at the first 10 rows here, we see the payoffs are in dollars. To get the odds, which I will generate, and I'm going to use a double. I'm going to generate a double variable to make it as precise as possible. Let's call it odds equals that payoff divided by 100. And when I do that, I see that I've converted the payoffs to odds. And I can actually follow along with the example in the paper. They were looking at the New England Patriots. And sure enough, we have here the odds of the Patriots winning were 8.5 to 1, just like they said in the paper. Next, we want to back out what the implied probability of the New England Patriots, and in fact all teams, was in 2013 at the beginning of the season when these payoffs were taken. And to do that, we want to use the same formula they did in the paper by calculating the probability, which I'm calling here prob, just so I don't have to write the whole word, to be 1 over 1 plus whatever those odds are. Now here you see I wrote if odds are greater than or equal to 0. Now why did I do that when these are all clearly positive? Well, I noticed there was actually negative odds in one of the teams in the NBA. I'll come back to that when we get there and tell you how to deal with that. For now, if you don't have this if statement, your odds will still be correct. And actually, let me just make sure they're all positive before moving on. I'm going to say, I can actually say summarize odds. Let's just make sure the minimum value is 6. Okay, so we're good. So I could have just written this formula like they described in the paper, and we would have been fine here with this data. But I'll return to that when we get there. Now what we want to do is remove the juice from these probabilities. Because if we look at the probabilities, they do look good. Since we use double precision, there's a lot of decimals. So we're storing these numbers as accurately as possible. And if we add up all the probability of each team becoming a champion, it should sum to 1. We should get an odds of 1 or a percentage of 100%, right? Well, I don't think we're going to get that. Let's check. You know, we can use egen to get a total of a variable. So let's make this test variable. Let's do this. I'm going to generate a double variable called test. I'm going to use egen. I should say egen instead of gen. And test is going to be the total of those probabilities. Now, as you can see, if I add up all those implied probabilities, I get over 100% or over 1. That's not possible. That 0.294637 is the juice. That's arising because the casino is not paying the gamblers a fair bet. Of course they won't. If they did, they wouldn't make money. So what we're going to do is spread that evenly, or proportionally, I should say, across all teams, and adjust the probability so that they do add to 1. And there's a couple ways to do this. But to show you the calculation going on here, I'm going to do it sort of a brute force way. What we can do is take each probability and divide it by this sum of probabilities. And what that's going to do is that's going to reduce this number because the denominator will be greater than 1. But after we do that for each probability, they should all add up to 1. So I could generate, let's call it prob no juice. That's actually a long variable name. Let's just say no j maybe. Obviously you can call it whatever you like. But let's have that equal the probability divided by that test variable. Maybe I should have named it denominator. And now let's see what that gives us. So all the probabilities did decrease. They should add up to 1. We can test that. But notice here the New England Patriots have an implied corrected probability, or a no juice probability, of essentially 8.1%. We have to move the decimal to convert that to percents. And if you check table 1 in the paper, that's exactly what they displayed, 8.1%. So we're looking good. Now there's a quicker way to do this. There's an egen function, PC, that will calculate for any variable what percent the value is, for example this value, of the total, which is exactly what we did here, because we divided it by the total value, or the sum. I won't show you how to do that here, but you should be able to look up in the help file how to use that option, or that function, and do this yourself and check that you get the same number. It's a quicker way to do this. But let's check before moving on that we've actually accomplished what we thought we did. It's always good to check. Don't assume you did it correctly. Those corrected probabilities should add up to 1. So let's let's egen, let's call it test 2. It's our second test. And that'll be the total of the probability with no juice. And now when I look at the data, indeed I get 1. And I should, because those probabilities should all add up to 1. But it's important to check that before moving on, before assuming I did it correctly. I want to know for sure. Otherwise, everything we do after this is incorrect. Okay, so that gets us past step 1. I suggested the first thing you should do is make sure you can pull out the implied probabilities without juice. And I suggested to do it for this year in this league because that was the table that was displayed in the paper, and we can check and make sure these numbers are the same. And now that we've checked and we know these numbers are the same, we can confidently move on knowing that at least we did this part correctly. But now what we want to do is calculate that competitive balance measure. But we already know how to do that from the last video. We did it by hand, and then I also showed you how to simply do it with the summary command. Since we've already done it by hand and we're certain that the summary command gives us the correct answer, we can just go ahead and use that here. So all we really have to do is sum that probability with no juice, and this standard deviation right here is our answer. Now if we compare that against figure 1, we see that NFL is represented by triangles, so that should be right around here in 2013, which is right below 0.03. And indeed, that's what we got. We got something just below 0.03. So again, it's looking good. We got 0.028 something. And so we can move on confident that we got the correct measure. Okay, now we know how to back out from payoffs the implied probability of every team winning the championship. We already knew how to make that a competitive balance measure. It's just the standard deviation of all of those probabilities. What should we do next? Well, first, perhaps we should save all the syntax we just wrote that worked in a do file. So I'm going to select all the commands that I want to use. This was just looking at the data. We don't have to run that. I suppose I'll keep the keep if league is NFL in 2013 for now. Obviously, we're going to drop that. Generated odds, generated probability. I guess we should keep the test because we used that as a denominator. There's our probability without juice. This test was just for checking, so we don't need to keep it. and we sum the probabilities so that we could see the standard deviation. So when I right click, I could say send to do file editor, and I will pull this into the screen. How do I put that on the file? I'll just drag this over. You see it's copied all of those commands. So if I click do, oh, it doesn't like that because we didn't save our data, but that's okay. We don't want to keep it. So what I'm going to do at the top, I'm going to write clear as a command, which will get rid of the data that's in memory if there's data already in memory. Okay, now I'll click it and it runs all the commands in less than a second and we go straight to the answer. All right, let me close that. We'll save that, just put it to the side. And now let's think about moving forward. So we have what we need for a single league in a single year. Let's now calculate this measure for all years of the NFL so that we can graph that time series line that we just saw in figure 1. So at this stage, maybe I want to work with this do file actually. And instead of keeping only the NFL in year 2013, I'm actually going to delete that portion and just keep anything that's NFL. So I can rerun this to get back to where we were. You see the standard deviation changes because now we just calculated it for all years, which is not what we want to do. But we did want to keep all years in the NFL. So let's take a look real quick. If I tabulate year, I do have all years. I have 32 observations, one for each team in the NFL. And the NFL is the only league we have. So this is what we want. Now we want to calculate the measure for each year separately. You've learned how to do this, how to do a command in Stata separately for each value of a variable. Here the variable's year. We want to calculate this standard deviation of implied probabilities separately by year. So let's think about how to alter our code to do that. What we want to do moving forward is check that each line is still correct in this do file when we're handling a data set that has multiple years. Some will need to be altered. Some we will need to tell to do these commands by year separately. That's not true for generating the odds because we want to pull out the odds from each row. Each row is a team year, and we still want that to be done to every row. Same thing for the probability. We convert the odds to probabilities. The test variable here, which is actually, we should rename it. It's the denominator. Let's rename that to denominator. That one we should do separately by year. When we only had 2013, we generated that as the total or the sum of all probabilities, but that's a year by year calculation. Those probabilities will change across year and they should sum to 1 within each year. So what we'll do is we'll add to this line by sort year, colon, and now that command should be carried out separately by year. Let's go ahead and run the data down to that point. I can highlight everything down to that point and click do. And let's take a look at what we've got. So I have the same denominator for 2013. That's the one we've already calculated. However, if I scroll down, you see as soon as we hit 2014, we have a new denominator, as we should. So I'm just checking here to make sure that we did a year-by-year calculation. And this is way faster than opening up each year separately and doing these calculations. We can do it all at once here with the by sort command. So now when we remove the juice from all of these probabilities, we'll be doing so according to the year. So we're spreading that extra 0.29 proportionately over the 2013 probabilities. And in 2014, we have to spread 0.375 something over the probabilities. So looking at the code, I think we're good to leave this because now denominator is a year-by-year variable, which it should be. So we can divide each probability by the value in denominator. And now if I summarize this probability without the juice, it's still giving me a value in total across years. So maybe I want to say by sort year, summarize probability with no juice, because we should have a different measure for each year. And now all of these different standard deviations across the year are going to be our competitive balance measure. And you can see we get the same one for 2013 that we did before. Now, this is nice. However, we want to plot a line that consists of only those values. And right now, if I look at my data set, it's pretty big. I have 192 observations. Each row is a team year. What we want to do is collapse this data set down to one that's just a year per row. And the only variable we really care about to make this figure is the competitive balance measure, or the standard deviation of those probabilities without juice. Now, we've collapsed data before, and if you look at the help file for collapse, you may recall that if we use collapse without specifying what we want, it'll give us the mean. That's the default. It'll give us the mean or average value of each variable that we keep. But we can also specify that we want instead the standard deviation by using that option. So that's what we're going to do here. I will tell Stata to collapse this data set, and I'll put SD in parentheses, and then any variable I list after that will be collapsed into the standard deviation of that variable. So I'm simply going to write probability no juice, because that's what we want the standard deviation of. And then as an option, comma, I'm going to say do this by year, because we don't just want the standard deviation in total, we want you to do it separately by year. So when I run this command, Stata is going to collapse the data set by year, so we'll have one observation per year. And within each year, it's going to give me the standard deviation of this variable, which is the juice-free probability. Now let's take a look at that data set. It should be quite small now. We can just list it. And there we have it. Each row is a year. And the only variable we really care about is that competitive balance measure, which is the standard deviation of the probability with no juice. Now we might want to change this variable name, because it's no longer the probability. Now it's our competitive balance measure. There's two ways we could do this. One, we could do it now. I could say rename that probability, and let's call it Champ SD, because that's what they call it in the paper. But you can actually do this while you collapse. So let me show you how to do that. When we collapse, I could simply write collapse. We want the standard deviation of the probability with no juice. We want to do that by year. What I can do is I can tell it at this stage to rename it. And I could say, call this new variable Champ SD. And if I just write Champ SD equals, the second variable is the one that will get collapsed into the standard deviation, and this will be the new name. So watch, I'll run this do file. Take a look at the data. And there we have it. All right, we're making progress. Now we just want to make the graph. We only have NFL here, but that's fine. We're just doing one step of logic at a time. And if you recall, since this is a time series, we need to tell Stata that with TS set, and I'm going to tell it the time variable is year. And you can see when I do that, I said, hey, Stata, we've got a time series data set here, just so you know, because I'm getting ready to ask you to make a time series plot. You need to know what the time variable is. I'm telling you it's year. And Stata says, okay, the time variable is year. It goes from 2013 to 2018, and the delta, which means change, is 1 unit. So it recognizes that the unit of change here is 1 year. Now all we have to do is say, please graph this data. Actually, you don't have to say please. I can just say TS line, time series line, and Champ SD is what we want to plot. And there we have it. As you can see, there's year on the x-axis and our measure on the y-axis, which it's giving us the label. It's telling us that it's the standard deviation of the probability of no juice, or the juice-free probability, I should say. This is kind of ugly. This is not what you want your readers to see. They're not going to know what that means. So maybe we can use an option to change that. So I'm going to use the option Y title, and I'm going to write Champ SD in quotation marks because this is a string. We're writing characters. And when I use that Y title option, you can see it relabels the Y-axis for me. I don't have to do that to the X-axis because year is, well, what we would label it anyway. But if you wanted to, you can use X title the same way. Okay, so far so good. We haven't even needed to use anything new, I think. to get to this stage. So technically you could have figured at least this much out on your own. The next step in logic I would take at this point is to say, okay, I was able to get the juice-free probabilities. I confirmed they were correct according to the paper. I then calculated the competitive balance measure. We also basically was able to check that to the paper because they had it on the graph. We could eyeball it. It looked correct. We then figured out how to carry out that logic in Stata by year so that I could then make this graph for the NFL. Now we need to do all of that by league. So whenever I have to add a layer of complexity, a by, usually I do it one at a time when it starts to get complex. Here, I didn't do 2 years at a time. I did all years. Doing it by league, well, I suppose we could do it all at once, but it's getting complex. So perhaps I'll just add one more league and take a look. So let's return to our do file. And now, instead of keep if league equals NFL, I'll say or league equals NBA. Let's keep 2 leagues. So I'm just going to run that portion. And let's take a look at the data. Indeed, I have 2 leagues. I have 62 observations per year. There must be 30 teams in the NBA because there's 32 NFL teams. And if I want to tab league and year, it might be too big. Nope, it's fine. We see that there's 30 NBA teams per year, 32 NFL teams per year. Everything looks good. All right, back to the code. Can I still run this line one row at a time? Well, yes, because we're just taking the odds and divided by 100. So that is a row by row operation. That should be good. Same thing for the probability. Although here, I believe this is why I started adding this correction. So let's look at this real quick. If I summarize payoffs, you notice the minimum is now negative. Now this is something not discussed in the paper because it didn't arise in their example, but we should discuss it here. Let me count if payoff is negative. How many of those are there? There's 3. Let's browse if payoff is negative. Or actually, we could probably just list them. It's a small data set, I think. List if payoff is less than 0. As you can see here, there were 3 years for which the Golden State Warriors gave what appears to be a negative payoff. Now, it's obviously not negative. It's not saying if you bet $100 that the Golden State Warriors will win in these years, we're going to take $128 from you. That's not the way we read these. In Vegas, these odds are read as you have to pay $128 to win 100. So when the payoffs are negative, you kind of flip it. It's how much you have to pay to get 100, not how much you'll earn if you bid 100. So to be clear, in 2016, that negative 128, what that means is you would have had to have bid $128 in order to win 100. So you would have given Vegas 128. When Golden State Warriors wins, you get back 228. You get back your original 128 plus the $100 you won. Well, now since that's different, we're going to have to adjust how we calculate those odds, or those probabilities from the odds, I mean. That's why here I said if your odds are greater than or equal to 0, if we're not in this case, this is the logic. If we are in that case, however, we need to do something different. So actually, let's go ahead and run this line of code. And you see there's 3 missing values generated for these 3 observations. Why? Because I said only do it if the odds are positive, and they're not here. So let me list those 3 again, actually. And as you can see, we did not calculate a probability for them. But if I list any others, let's say the first 5, we do have the probabilities. Or the juiced up probabilities, we could say. So what we want to do here is write a separate code to replace these missing values with the implied probabilities. And what I'm going to do here is I'm going to say replace the probability with the absolute value of the odds. So instead of 128 or negative, I'm going to use the absolute value. That's that ABS and odds in parentheses. Give me 128 divided by the absolute value, so that 128 again, plus 1. Oh, I'm sorry. By 128, I mean 1.28 because we're looking at odds. So I want to take away that negative, and I'm going to say we're putting up 128, and we're getting back basically 228 because we're going to have that 1.28 plus 1, so it's going to be 2.28. So it is the same logic, we just have to write it differently because now we're saying how much you have to pay to get 100. So the payment is on top. Before we had a 1 here because you were paying 100 to win. Now we have the odds because it's representing what you have to pay. So it's the same logic, but we do have to put in a different variable because of the way the variable is constructed. So now when I list those three variables, or those three observations, we see 1, the implied probability with juice, but 2, we also see why they were negative. These probabilities are greater than 0.5. That means that the most likely scenario was that the Golden State Warriors were going to win in these years. Not very competitively balanced if we're more certain than not of who's going to win. But then again, that does make sense. That's why you would have to pay more than 100 to win 100, because this thing is probably going to happen. Okay, so now that we've done that correction, let's move on to the next line. So here, we calculated the denominator by year because we had 6 years of NFL data and we needed 6 denominators to pull out the juice. We still have those 6 years of NFL, but we now have 6 years of NBA as well. So we don't just want to do this by year because that would combine, for example, 2013 NFL and NBA. We want to do it by league and by year. So the only thing we should have to change here is by sort league year. You can use 2 variables. This is fine. I'm not sure if we've done this before, but just so you know, this is a completely legit thing to do. Let's go ahead and run that and see what we get. Let's take a browse. And it looks like the NBA denominator for 2013 is very similar to the NFL's. It's kind of suspicious. Let's keep moving. 2014 is different. I think I recall the NFL's went up, this one went down, so I'm pretty sure we're not doing something wrong here. But just to be safe, let's remember this 1.294, or actually an easier way to do this, to make this comparison would be to say browse if year equals 2013. I want to make sure those aren't the same. So there's NBA, here's NFL. Ooh, they're very, very close. Look at that. And maybe they should be because they're in the same year, around the same time, not exactly. So you would expect the juice that the casinos are getting would be about the same. They might have a reason to have a higher charge or a bigger fee or a bigger spread between what they offer you and what's fair across leagues. But it does make sense that these are very similar. But as you can see, they're not the same. So we do have denominators now that are specific to year and league. That's what we want. So since those denominators are specific to our year and league, this line should be fine to run. And now maybe what we want to do is by league and year, go ahead and just show ourselves that this is different measures. So these competitive balance measures, these standard deviations, should differ across league and year. So let's look. The 2018 NFL is 0.025. Let's see what 2018 is for NBA, 0.10. Those are very different. So it looks good. What we want to do now is collapse the data set basically into one very similar to what we're staring at, right? We want one row to be NBA 2018 and then give us the standard deviation value. So what we say here is we're going to collapse. We do want the standard deviation of the juice-free probability. We're going to rename that variable the champion standard deviation. But instead of doing it by year, we're just going to do it by league and year. So I'm just going to run that whole do file, and then let's take a look at the result. There we have it. We've just done this operation by league and year separately. Now here's the problem you're going to run into. Here's something new you're going to have to figure out. So I guess for those of you who tried to do this on your own, maybe this is the stage you had to come back to the video for. Although I think I told you what to look up in the PDF to figure this out, so maybe not. Well, in any case, whatever the reason is you're here, I'm glad you're here. Let's talk through this. If I was to try to plot two time series lines, well, I wouldn't even be able to tell it to plot, because as soon as I say set this data to be a time series data set, Stata gets upset. It says there's repeated time values in the sample. It says this is not a time series because you have 2013 here and here. If it was a time series data set, you would only have one row per unit of time. And so Stata's right. This is not a time series data set anymore. We have multiple time series. When you have multiple time series in your data set, that's called a panel data set. The panel variable distinguishes each separation. So here it's league. So we have an NBA time series and an NFL time series. Therefore, the variable league is called our panel variable, and year is still the time variable. Essentially, we just have multiple time series. Well, we can tell Stata that by using the command xtset. Xtset says this is a panel data set. X is the panel, T is the time. So since X is listed first, we tell it league is our panel variable, and then year is our time variable. And I misspelled league, as I typically do. So let's try that again. And even when we do this, we get a new error. It says you can't use string variables, and league is a string variable. So Stata doesn't like it when your panel variable isn't a number. Now what we're going to have to do is convert those strings into numbers. Now, you might think, well, okay, I could just generate a variable, tell it to equal 1 if it's NBA, 2 if it's NFL, and when we do the rest of the leagues, we can do it for all of them. 3 and 4 as well. But there's a really easy way to do this because it turns out this is a common operation in data science, is to convert a string variable to a numeric one. And you've seen variables like that before. The way we do that is to use a command called encode. So I'm going to open the help file real quick. Encode changes a string variable to numeric. All we have to do is say encode this variable. So for us, it's going to be league. We want to change it to a number. And then generate some new variable. So this will literally just take a string variable, create a new variable that's a number, and the numbers change when the string variable changes. It's very simple. So here I'm going to write encode league, change this string variable to a numerical variable, and let's generate, I'm just going to use the capital letter L so I remember it's the league. Now when I look at the data, see this variable has the same values as league. So what's the difference? Well, if you browse the data, you'll notice they're different colors. This is a string variable. When I click the cell, I see NBA up here. This is actually numeric. It gives me the number 1. This is the number 1. What we're seeing in blue is the label. So Stata does this very useful thing. It converts those strings to numbers, but then saves the string as the label so that the user, you and I, still see what that represents. This is very useful. So now let's go back to tell Stata we have a panel data set. I'm going to say xtset, capital L, because that's our league variable, that's numeric, and year is our time variable. Now Stata's happy. I'm happy. We're all happy. The whole world is happy now. Stata says, okay, we got a panel variable. It's L, and it is strongly balanced. What that means is that for each level of L, so here NBA and NFL, you have the same number of years. Your year observations are identical. We have 2013 to 2018. And again, the delta or the change is 1 unit, meaning each unit is a year. So this is great. Now Stata knows that we have multiple time series or a panel data set. Now we can go ahead and graph both lines on the same graph. And if you recall, the way to do that is to use the command two-way, and then in parentheses, we will write each individual graph. So let me go back to, I didn't save our graph, so I'm going to have to write it here. We want a TS line, and we want to show the champ SD measure. And I'm going to say here, if league equals NFL. So let me do that simply. We get the same graph here. Oh, and I might want to change that Y variable. Let me do that. That Y title. So after if league equals NFL, I'm going to write comma for options, Y title, and inside there I'm going to tell it, let's call that champ SD. Okay, So all I've done here is recreate the graph that we've already made. So even though NBA is in there, we got a panel data set, I said we'll just graph the NFL stuff. And as you can verify, that's the same. Now I want to do that for the NBA as well. Oops, change that. So I'm just going to click the same code I wrote down there, and I'm going to copy this parentheses. And instead of NFL, here I'm going to say NBA. And actually, since I've already specified the title and they're on the same graph, I don't have to specify that again. Just to remind you, what we're doing here is a two-way graph, two-dimensional. When I write things in parentheses, it's saying do more than one graph and stack them on top of each other. So this could have been its own command. This could have been its own command, but we're doing them both together. But since they're sharing axes, they're sharing the same graph, I don't have to write Y title over and over. And that's true for any option you would use for the visual display of the graph. So now when I run the code, look what we get here. We get them both at the same time. It's beautiful. Now you're going to want to try to look up how to handle the legend here. This isn't very descriptive. We want, obviously, the red one to say NBA. We want the blue one to say NFL. I'm going to let you figure out how to do that. You're going to want to look at the two-way command we just used, and then look at two-way options. And then at some point, you're going to find legend options. It's a bit of a rabbit hole, but it's something you need to struggle with, because this is the way we learn. This is the way we do research. You also, for bonus points, if you want, might want to figure out how to use squares and circles like the paper did to make your graph look as similar to theirs as possible. If you look at this graph and their graph, you'll notice they were actually both made with Stata. So it is possible for you to completely recreate the look of their graph. I'm not going to require that, obviously, but if you want to look into it and go down that rabbit hole, I will give bonus points if you can figure it out. But for everybody else, if you don't care about bonus points, this is good enough once you figure out how to replace this with the league names. That much I want you to figure out on your own. Well, let's check one more thing before signing off. We just verified that I can do this by league and by year. There's no reason why I can't just add 2 more leagues here. There shouldn't be any other codes that I need to adjust. So let's do that. I'm going to completely get rid of this line that says keep only 2 leagues. We don't need that. Oh, and we might want to add the new commands, xtset capital L in year. And of course, we need to generate that capital L. To do that, we said encode league, give us the variable L. After that, we made our two-way, and that's a lot of typing. So actually, let me copy that down. And we will have to type more here because it looks like we did have to do NFL and NBA by hand. But let's just go ahead and run this with all 4 years and see if we can get the same graph with 2 leagues. Sure enough, we get right back to our answer. And notice, that took less than a second to do all those calculations and the graph. It's pretty amazing. Okay, so what we want to change here is we want to add 2 more leagues. We should have MLB and, oops, got an A there, NHL. These are our 4 leagues. So let's just run this line and see what happens. This is what your image should look like at the end. But again, I want you to figure out how to change all 4 of these to label which league is which line. For bonus points, you can do the shapes. And I would say for bonus points, you can make it black and white like they did. That's what you have to do to publish in a journal. But I actually don't care about that. I hate the fact that journals are publishing in black and white. There's no reason not to use these beautiful colors. It's easier to read. And for more bonus points, if you like, go out and get new data, either years that aren't included here or leagues that aren't included here, and redo this entire assignment. Calculate the competitive balance measures across year for different leagues or different years or both, and show me what that looks like. Now, one of the beauties of this measure that they didn't mention in the paper or even make use of is, since this is using gambling odds, we can apply this to leagues that have ties. We could apply this to soccer. We don't have to make any additional adjustments. The probability that a team becomes a champion has nothing to do with whether or not the league is only win-loss or win-loss and tie. In that case, feel free to go out and do any European, Asian, African, whatever soccer league you want. You could do the national teams. You could do the World Cup championship probabilities. Just have fun with it. It will be bonus points. You don't have to do it. But if this is something you find interesting, and I hope you do, I strongly encourage you to go out and do this again on your own for leagues that you care more about. The website you can get the data from is listed in the paper, but there are other websites that you can find if that website doesn't have the leagues you're interested in or the time frame. You can find this data in other sources, but that is a really good source. The data we used here came from that website, and what I did was I used the last reported odds in the preseason before any games were played. Let me show you where I found it. Here's the website that they got the data from, and so did I. For example, if you go to NFL, we were looking at champion odds only. We only wanted to look at the odds of winning the championship. We're not interested in individual game odds, just the odds that you become champion. We get these nice little tables here that we can look at year by year. So for example, let's look at 2021, where the Los Angeles Rams combined with the referees to beat the Cincinnati Bengals. And what you'll get is the payoffs here listed for each week. They don't have preseason. The data I got had preseason. So what I would do is, if this is what you're looking at, notice that it says this is the payoffs for the regular season prior to week 1. So this would be the last odds before the season began. I would just take this column and use that for 2021. As you can see here, the year the Rams combined with the referees to win the Super Bowl, which was last year, you would have won $1,200 had you placed a $100 bet at the beginning of the season. Over time, it went down a bit, and then went down a lot, and then came back up, which is really interesting. So you could have gone until the very final week and still won $900 from a $100 bet. Just out of curiosity. Bengals were $15,000 if you would have bet 100. Those are some juicy odds. And it doesn't matter because the referees didn't want it to happen. The league obviously wanted LA to win in LA, and there was obvious market incentives to do so. But that's my opinion. That's not a verified empirical fact, but it is my story and I'm sticking to it. Okay, I hope this was very helpful for you guys. Have fun with this, and I look forward to seeing information on other leagues for those of you that do pursue the bonus points.